Hello. In this video, I'm going to demonstrate how to set up the EBSD software to conduct EBSD analysis on a sample. Um, this is not going to be every single feature that you can do with EBSD analysis, but I'm going to try to demonstrate a lot of the critical steps that are used for, um, for routine EBSD analysis. The sample that I have, first of all, this is being done on an FEI Helios 650. This is a dual beam fib instrument, and the sample that I'm using is a uh, copper TEM half grid, and I've used the fib column to cut off the end of the copper finger here, and we're going to do the EBSD training just on this surface. I like using these because they're very easy to prepare. They produce good quality patterns. They have small grain size, and it's very, very consistent. Um, Obviously, you're going to be doing EBSD on your own samples, but hopefully, what you see here will help you in your experimental setup. The EBSD camera on this particular tool is made by EDAX. It's an older Hikari camera. It can run up to about 450, 460 frames a second at its maximum speed. There's certainly newer cameras out there that you can buy, but this one still works pretty well. The software we're going to be using to control the EBSD camera is called TEAM. This is also made by EDAX, and I will be going through a lot of the parameters in how to set up the camera and how to set up the analysis. So first things we need to do is we need to configure our microscope for EBSD. Um, right now I'm imaging with 5 kV acceleration voltage, 0.40 nanoamps. Um, EBSD generally needs a much higher beam current than this, and it generally needs a higher acceleration voltage. In theory, you can do EBSD at any voltage you want. Generally, we operated at 30 kV on most samples. Or at least higher than this. So I'm going to turn my voltage to 30 kV, and I'm going to turn the beam current up, and I'm going to go just for a starting point here. Let's go to 13 nanoamps of beam current. Not the highest beam current on a Helios, but this should be pretty reasonable. All right, let's make sure our image quality is good. We're going to focus, adjust astigmatism as needed. Make sure on your SEM you check your gun or source tilt alignment so that you're getting all the beam current that you want. All right, now on this particular microscope chamber, the EBSD camera comes in from the right-hand side. I need to rotate my sample so that it's pointing at the EBSD camera. I'm also going to change my working distance. Right now I'm at a 4 millimeter working distance because I was using the fib column to cut off the end of the grid. Now I've already found these stage positions, but in your tool you would have to rotate and change around. So I'm just going to click on my EBSD position. Now my copper half grid is mounted on a 45-degree surface on this pre-tilted stub. I have it attached with silver paint. And because it's on a 45-degree angle, I only need to tilt the stage another 25 degrees, and that will allow the cut surface to be at an incline angle of 70 degrees. Um, there's no rule that you have to do EBSD at 70 degrees, but traditionally it's always been done at 70. If you don't have a pre-tilted stub and your sample is flat, you can do EBSD on the top surface by tilting to 60 degrees. Or if you have a stage that goes higher than 60, you can always use that as well. The Helios stages only go to 60 degrees as a maximum, and EBSD works quite well there. Um, all right, so I have my SEM image here already. Again, I saved this position, so we're right here. I'm going to zoom focus a little bit, make sure my astigmatism is adjusted. Okay, now I want to make sure that um, this the SEM is going to focus and follow this plane. So I'm going to turn on dynamic focus. So on this tool that's in the tilt correction tab, I'm going to turn on dynamic focus. And now by default, this tool is focusing on the 25-degree plane because that's what the stage tilts at. So I need to tell it that I have a pre-tilt angle of 45 degrees. And then now my dynamic focus plane is actually following the plane of this cut. Okay, so now let's go ahead. I don't think I need to do much more with the FEI software. I'm going to switch my display over to the team software, and then I'll show you how to set that up. All right, so this is our EDAX support computer. We're going to start this program called Team. Just double click on it, and it'll start up. You can see the current the version that's on this tool is Team version 4.5.1. This is the most modern version that works on this particular instrument. They do have newer versions of Team. There's a 4.6, probably 2, or maybe even newer than that, that you may be using on your own system if you have a more modern PC. But on this tool, this is the most modern version that we can run. Hopefully you'll see that Team hasn't changed much over the years, and most of the features are going to be the same, regardless of your version that you're running. When I started up Team, I don't know if it came through on the audio recording, but the slide motor homes on the EBSD camera, so you should hear that sound. If you don't, it generally means there's a communication problem with the EBSD camera. So just something to be paying attention to. And eventually this will boot up. Team has always had a little bit of a problem when it comes to loading. It's always been slow for years and years. I don't know why they can't make it faster, but it usually takes a couple minutes here to start up. Okay, so now we're running in the Team software. We have to log in. Uh, at our lab at the University of Michigan, we operate this tool with a single login for all users. If you're running this at your own lab, you may have individual usernames for every user of the system. It's going to depend on how it's configured. But in our case, we're going to just log in with our account. Now, I put in my user account, and it says that for for this particular account, we have these different functions available. We can do EDS, we can do EBSD, we can do team mode. Team mode is both EDS and EBSD at the same time. That can be useful if you have samples with 2 phases in it. And then we also have the Atom Probe Assist option on this tool. This is more or less a specialized transmission EBSD mode or TKD mode. To be honest, I never use this one. If I'm ever doing work on atom probe samples, I generally just do it out of the EBSD mode, but that is a feature. So we want to click on which technique we want to use. So I'm going to click on EBSD, and you can see it doesn't really tell you very well which one you clicked. So just make sure, if you're not sure, just click on it a couple times. But we have EBSD selected, and then we're going to click Login. So the next thing we're going to do is we have to create a project. If you've already had a project in here, it shows you the recent projects, but you can always click on the EDAX Explorer, and then this lets you look at all the projects that have ever been done on the tool. Or we can click on the project button, and we can make a new project. So we're going to give it a project ID. Let's just call this training setup sample, or it doesn't matter. It's training sample. Actually, I'm going to say training one. We'll just call it training one. Now, the database on Team can track multiple samples. So we're going to start off with just sample a sample ID. The default just says new sample. I'm going to just change this. I'm going to say copper, let's call this copper post 1. And next, we're going to tell it what structure file to use. So I'm going to click Identify Structure of Interest, and it brings up a periodic table. On this particular setup, by default, it loads a face-centered cubic and a body-centered cubic structure file. This will possibly work for your samples if your samples have these structures, but I always get rid of these and I load the correct structure file for your given material. So if I click on face-centered cubic, there's a remove phase button here. I can click it and I can take off the FCC, and I can click on the body-centered cubic and I can remove that one as well. So now I don't have any active phases in my list. To search for a particular element, I'll just go up here and I can pick based on composition. So if I say change all to no, and then I'll click on copper as a maybe, or I could say yes. It doesn't really matter, but I have a maybe and I click search, and then the database pulls up all results that have copper in it. In this case, only copper, pure copper. So I'm going to click on this, and then I'll click the little arrow, the right arrow button here, and that's going to transfer copper to my active phase list. If you have more complicated material systems, you can always search by more elements. So for example, if you have, say, a steel sample that has austenite or martensite in it, if you search just with iron, you'll get all of the iron-based systems. But you can also say search iron and nickel together, and that will give you, sometimes it'll give you the better result, especially if you say, if I make everything yes. So I say I want iron and only. Sometimes on older systems you wouldn't get the austenite phase. It looks like I got it here, but um, on other tools I've run, you have to pick nickel and iron together, and then sometimes that gives you austenite. Anyway, you got to just play around with it till you find the phase that you want. In this case, it doesn't really matter. We're not running steel, but we have our copper phase already in here, so that's selected. If you can't find the structure file for the material you want, you may have to import it or build it yourself. There is a add phase button down here where you can either import the structure file from another database, or you can build your own file. I'm not going to go through the specifics on this, but just to show you, you can open up the build and you can load in the space group that corresponds to your material, and then you can list out the atomic positions for each of the elements in the structure, and then the software can generate the various reflector planes for that file, and then you can use that. Now I don't want to, I accidentally just added this new phase, so I'm going to click on it and say remove because I don't want that in there. If you want, I can click on the phase that I have, and over here on the right there's this little phase info, and you can pull this up and this will show you your lattice parameters, the reflectors that are built based on this one. You can have it use additional reflectors if you want. So right now it's only using a couple of the main ones, but you can turn on and off reflectors if you think that's going to help what you're doing. You know, you can look at if the structure file has some of these things in it, you can look at them like crystal view. You can see the wireframe model. So there's lots of stuff in here. So once I have my structure file, I'm going to click OK, and that takes me back to my project creation screen. And now I'm just going to click OK here, and we'll advance into the team software. Now, the way team is laid out is that you have a bar across the top with your data collection tabs. So we can do point analysis, mapping. You can do survey mode if you want to just explore the quality of your sample. It does have a simulation mode if you want to simulate what EBSD patterns look like in different orientations. That might be a useful tool. And then it has some data reporting features up here. On the left is your project content tree. So this was going to have our project ID here, so training one, and then our individual samples will be listed on this tree. And as we acquire data, that will show up underneath each sample ID. If you want to go to a different sample, you can go down here with these little buttons. There's a sample button. You click on sample, and then you can make a new sample. So for instance, I can say I want to go to copper post 2, and I can create that as a new sample. And if I want to use the same structure file that I'm using currently, I can say inherit structure from active and click OK. And now I have a second sample in my tree. To go back, I'll just click sample, I'll click post 1, inherit, and OK. And now I'm back on copper post 1. You can see it's got a little red flag on it that tells me this is my current sample. If I need to change my structure file, I can click on the profile button, and this brings me back to my periodic table and my phase list for the structure files. So you can swap these out, change them to something else uh, without having to recreate the project. If I want to change projects, I just click the project button, and then we can go to different projects. When we can import and export data. So if you're bringing the project data in from another microscope and you want to keep working on it, you can import the project file and then resume analysis on this. So for example, in our lab, we have several tools that all run EDAX TEAM software and have EBSD cameras. So you could do part of your analysis on one of the other SEMs and then import the file and continue work on this tool without having to make two separate uh, projects and then merge them together later. And then you can also export your data when you're done. The print function doesn't do anything on here because this particular instrument's not set up with a printer connected to it, but I suppose you could print results when you're done. Um, Up here on the top right is our user profile. So if you're in a lab that has multiple logins and you want to switch your user, you can go up here and click switch user. There's also some profile settings that are associated with this account, and you get to these by clicking on the little person icon right here. And then these are all the settings for your profile. For EBSD, I don't think there's much in here that you're going to have to look at. Um, Maybe the custom image folder. So when you're exporting image data out of Team, it's going to go to wherever this folder is pointing to. So a lot of times I'll point this to some default folder on our file server, so that I know where the images are going. So like for right now, let's see where it's going. Yeah, it's going to a students folder. So I can point it back to my temporary image folder that I normally use. So now if any images I export out of here will go to this folder instead of another user folder. You can change your formats for your images, TIFF. You can change your drive for where it saves the data. This is useful if you have multiple hard drives on your computer and you don't want to fill up your C drive. You can make sure that all of your data gets saved to another hard drive on the system, especially if you're going to save a lot of images. That might be a pretty big file. Um, anyway, let's hit OK. Oh, one other thing I like to mention, if you're this video is not for EDS, but if you are doing EDS at some point, you can change the quantification method. So the default is this EZAF, but um, depending on what you're doing, you might want to change it, but that's done in here. You can also change language if you want this in a different language, and you can add a image if you want like a picture to show up for this instead of this little default silhouette. You can do that. So we'll hit OK. Um, the last area that we want to look at is over here on the right. This pullout is the advanced properties tab. You're going to need to have this open quite a bit when you're setting up the EBSD camera. So each of these little sub-tabs is got parameters in it that we'll have to tune. So this is the settings for the EBSD camera. We also have our camera position, which is we'll use to insert the camera, image area, the settings for the Hough transformation. All of these are useful for EBSD. So the first thing we're going to do is we have our sample in a safe location for inserting the camera, right? Just to confirm, if I go back to this view, our sample is tilted. It's important that the stage is tilted. So when the camera comes in, it doesn't run into the sample holder or to the stage plate. Um, you almost always have to have some kind of stage tilt. So even though we're using a pre-tilted holder, we tilt the stage a little bit. That's for safety. If you, for some reason, have your sample on a 70-degree pre-tilt holder, you need to make very, very careful analysis of where everything is so that the EBSD camera doesn't crash. It's generally safer to use a lower angle pre-tilt holder so that you can tilt the stage towards the camera, like I have here. I have my working distance at the moment is down at 10 millimeters. EBSD generally works better at a little bit longer working distance. We can operate it at almost any distance on this tool. Like we could do it at 4 millimeters, we could do it at 20 millimeters, but somewhere like 10 to 20 millimeters is generally a good range. It's going to depend on where your camera is, but uh, on this tool that's usually a good target, 10 millimeters. All right, so let's go back to our software for team, and we're going to insert the camera. So I'm going to open up the advanced properties, and I'm going to go to camera position, and I have a retract and an insert button here. Now these buttons they either fully insert or fully retract. The buttons down here move it by a small step. So if you want to back the camera up just a small amount for some reason, you can do it with these little buttons. There is a touch sensor on the end of the camera. If that activates, you may have to, well, first, hopefully it doesn't activate, but if it is turned on, you can click the reset touch sensor and that unlocks the camera movement again. So I'm going to click insert, and the software pulls up a warning and it says your stage tilt is less than 60. Do you want to move? And I can say yes or no here. The reason I'm getting this warning is because I did not tell the team software that my sample is on a pre-tilted holder. So if I say no, and I go to a different tab here, the image area tab, uh, I can see that the software reads that my stage is tilted to 25 degrees, but it thinks my pre-tilt angle is 0. So if I change pre-tilt to 45 degrees, now the summation of these two is 70. And if I go back to camera position, this time if I click insert, it should not complain. So I click insert and the camera starts going in. Now while it's moving, there's a stop button right here. There's also another stop button down here on the bottom left. I don't know why it goes down here on the bottom left, but that's the other stop button if the camera is going to hit something. While the camera's moving, it's a really good idea to go back and look at your CCD camera. And this way hopefully you can tell if the front of the camera is going to hit your sample. The touch sensor, by the way, on this particular camera is this little brass plate hanging off the bottom. And a lot of times the camera screen itself will hit your sample before the touch sensor hits anything. So you can't rely on the touch sensor to stop the EBSD camera insertion. You need to be really, really careful here. Now, I have a lot of space. This should be safe. If you have a much bigger holder, you need to be very careful that you don't crash anything into this screen. They're very, very fragile. They're very easy to break. Okay, let me just double check my position here is good. Make sure my focus didn't change too much. Sometimes the insertion of the camera will shake everything a little bit out of position. Doesn't look like I polished that very well, but hopefully it'll be good enough for what we're demonstrating today. So I'm just going to set my field of view on my SEM. Just zoom in a little bit here so I'm imaging just the surface of the copper. And then let's go back to the team display. Okay, so the first thing we have to do is set up the camera. Now I have my SEM. My SEM is live. It's scanning on the surface, and it's scanning at a relatively fast scan speed. And I know at least on this sample, I know that I have lots of different grains in the field of view. You generally want many grains to be imaged all at once. In the help manual for team, it says 25 grains at a minimum, but more is always better. If you only have a single grain in the field of view, you can't set up the background subtraction correctly, which I'll show you what I'm talking about here. So now we're going to go to the EBSD Camera tab, and this is going to show us the live display of our EBSD camera. Now, hopefully you can see something here. Now, this is using the settings from the previous setup. So whatever the last user setup here is going to be applied, which generally is not going to be correct for your session. I'm going to show you how to set it up manually. I think it's more helpful for a lot of difficult samples to do it this way, but I'll also show you how to use the auto function on here. So the first thing we're going to do is we have to remove the image processing recipe. So right here where it says image processing and it's on standard, you always have to go back to none as your first step. That removes all of the background subtraction from the live image. And if you forget to do this, you'll have a really hard time setting up the camera. So now we have just the raw image on our EBSD camera. The two controls we want to look at next are going to be the exposure settings and the binning. Camera binning is going to allow us to group pixels together on this display to make larger virtual pixels. And what that does is it lets us run quite a bit faster. To show you what I mean, if I move my exposure knob all the way to the left, so this is the fastest exposure that the camera can operate at, and I'm using a 5x5 binning right now, and I can run at about 258 frames a second. If I change my binning to 6x6, now my maximum frame rate jumps up to just under 300 frames a second. And if I go up to the 10x10 binning, now I can run at the 450 frames. Oop, my exposure went. I need to make my exposure at the 0. Okay, this is now the fastest that this can operate at, 460 frames a second. However, as you change your binning, it does make this image get more and more pixelated. And on a really good quality sample, it will still work. But on most of our normal samples that students run here, you won't be able to get a usable pattern if you're using these really extreme binnings. Newer cameras also can go to higher binning. I think the other camera in our lab can go up to, I think, 20x20 binning if you want to. So don't assume that just you only get these particular numbers. It's dependent on the model of the camera. The other thing to be careful of is that the optimum binning will change with different cameras. So a 4x4 binning might work really well on this particular Hikari camera, but on a newer Hikari, you might want to run 6x6 or 8x8, and you'll get the same quality. It has a lot to do with the pixel size of the camera. So just be careful with that. Don't automatically assume that you're going to use the same binning on every instrument you ever use. You need to optimize for each camera. I'm just going to leave it on 5x5 binning for now. That's a kind of the default value in this software. It always starts out at 5.5. The next thing we want to do is set our gain and exposure. Exposure time is going to significantly affect our frame rate. So if I raise my exposure time up, my frame rate drops. This is because our frames per second is limited by the time of the exposure. Now, if I drop my exposure all the way down, at some point here, my frame rate is limited by the processing speed of the camera, and it will not change. So at zero exposure, or essentially zero exposure, I can get 258 frames a second with this particular binning. If I raise my exposure up just a little bit, you can see that my frames per second does actually stays the same. So I'm still limited by processing speed at this point. Now, if I keep going up with exposure, eventually I'll find a point here where my frames per second start to drop. Let's see, right about, it's usually, okay, right about, okay. So now I'm running 230 frames a second. So now the exposure time per image is longer than the processing time. So now my frames start to decrease. If you want to run the fastest possible setup, I usually try to set up around this transition point where my acquisition speed is processor limited and not exposure limited, and that lets you run as fast as possible for a given bin. Now, this is still kind of dark. In order to increase the intensity on the image, I can use my gain slider. So if I add gain to the image, I increase intensity, but gain will add pixel noise to the image. So be careful that you don't add too much gain because the image will look really bad and you won't be able to get index results. On this particular Hikari camera, we usually recommend that you keep the gain less than 10 or maybe around 10 or less. If you use higher gain, your image will be very, very bright, but it'll be so noisy that it generally won't work. Other Hikari cameras or other EBSD cameras, you may have to experiment a little bit to find out what levels of gain are appropriate. But the gain doesn't cost you a frames per second penalty like exposure does. So if you're trying to go really fast, then you want to use a little bit more gain so that your exposure is lower. What we're looking for is we want to be have the brightest image we can possibly get on our camera, but we don't want to saturate the camera display. So if I increase my exposure a little bit here, we can see that I have this intense white spot in the center of the camera. This is a saturation spot. It means my exposure is too high, and I will not be able to get any data in that region. So we want to turn the exposure down until that really, really intense white spot just disappears. Now you can run it in an underexposed condition, but it's just going to make it harder for the software to find the diffraction bands. So I usually suggest that you try to find the right exposure setting just below saturation. And you can tune that with either exposure or gain depending on what you're trying to do. Again, in this case, I set my exposure to so I get maximum frames per second, and then I'll use the gain to fine tune the adjustment. All right, so now my camera should be set up fairly well. This image, I don't see any diffraction patterns yet because I haven't subtracted the background. Now to acquire the background, there's a couple ways to do this. I'm going to show you the manual way first. We're going to go to the image processing tab, and there's a drop down here for the different types of image processing recipes, and right below that is the capture background button. You can specify how many frames you want to average for this. The default 16. I usually increase this quite a bit. What you don't want is you don't want to accidentally acquire a single pattern in a single grain. What will happen then is you end up subtracting the diffraction pattern, and then you'll get a false image. So as long as our SEM is scanning over a lot of grains and it's scanning relatively fast, we should be okay here. So I'm going to increase the frames a little bit, maybe 100, 150, and then I click Capture Background, and the software has now recorded a background image. Now it's not applying the background subtraction yet because I don't have an image processing recipe loaded. To load that, I can choose one of the pre-built recipes, either standard or enhanced, or I can choose custom recipes. I'm just going to click standard. And the standard recipe is a static background subtraction. So it's subtracting the pattern that I just acquired, and then an intensity histogram normalization. This is essentially a digital brightness and contrast adjustment for this particular image. Now, once you have your background subtraction done, you should be able to see the diffraction bands in the camera. Now, right now, my beam is scanning really, really fast, so it's sampling a lot of grains. If I slow down my scan speed on the SEM, I can now start to see the Kikuchi pattern show up as the beam is moving through the different grains. And that tells me that I've set up my camera fairly well. So now let's just acquire a quick map, just make sure everything's going well, and then I'll come back here and I'll show you how to use the auto functions for setting up the camera. So we're going to go up here to the top. We're going to go to the mapping drop-down tab. I'm going to click on it once, and this opens up three more buttons below here. I'm going to first do a SEM image. So the SEM, if I click on this, it'll take a SEM image. I can change my settings depending on what I want. I'll leave it at 512 by 400. The signal, this is if you have a forward scatter detector, or the ADC1 is the image coming from the SEM, so I'll just leave that. If I click on options or advanced, there's some things in here that you can turn on and off. If you click on the advanced button, it just opens up the tab to the right. And if we go to image area, we can change a lot of these settings here as well. So if you want to change like the image size, you can set it here. You can change the integration number. Currently, tilt correction is on, and the auto signal to noise is turned on. And what that means is that the software will adjust the scan speeds automatically based on the signal. Um, the scan speed in the team software is this integration number. So right now it's at 3. Um, if I turn off auto signal to noise, I can then put whatever I want here. So like if I say 50, it'll be a little bit slower scan. If I want a really slow scan, I could do several hundred or 1,000 maybe. Um, that's up to you to kind of play around with those parameters. And again, the pre-tilt angle is in here. So I'm going to go back up here. I'm going to click on image area, and it's going to acquire the image. And it looks like I need to do a little bit better job polishing this surface. I got a lot of little curtains here, but hopefully it'll run. So now to collect the map, I'm going to click on the Collect Map tab, which is now available. If I just hover the mouse over this, I can see all the settings for this particular map. You have a choice of resolution: coarse, medium, fine, or custom. Um, I'll just leave it on coarse resolution for now. And then for the camera, we manually set up the camera, so I'm going to leave it on manual. But if you want to use the pre-built recipes, you can choose these different options here, and then the software will set up the camera for you. So let's click Collect Map, and it starts acquiring the EBSD map. While it's running, you can change the displays down here. This little tool on the bottom left. You can turn on and off the different types of displays. So the IPF display is on right now, as well as the image quality. So if I turn off the image quality, which is in the grayscale, then we just see the IPF map. If I turn off everything, then we just see the SEM image. And I can also look at image quality in sort of a color view. I can look at confidence index. Um, I can also turn on and off the SEM image or the image quality map here, depending on what you want to see. Um, a useful tool I really like to turn on a lot is if you click this little Kikuchi pattern right here, this will show you the live display of your EBSD camera. And this is really good feedback to know if your camera is set up right. You can see your patterns show up. If you click on the little wireframe here, it'll show you your grain orientation based on this little cube wireframe model. This is kind of useful if you're trying to find different grains for, say, a TEM analysis. I find this very intuitive, that you just look for a grain where the cube is aligned kind of the way you want it, and then you go to that spot. Um, some of these visualization tools do have a processing time penalty. So you may find that your points per second, which is shown right here, this may or may not change as you turn these features on and off, because it does consume a little bit of your CPU to display those values. So just be aware of that sometimes you don't want that stuff displayed. It slows you down a little bit. Okay, so now we've acquired a map. I'm going to click Finish. And so we know that this area is okay for EBSD. Let's go and back to the camera setup, and I'll show you the auto settings. And maybe you want to use the auto settings, maybe you don't. I generally don't use them. I find that they don't always work well, but I'll show them to you here. So we'll go back to EBSD Camera, and if we want to use the these menus have a habit of closing on you unexpectedly. If we want to use the auto settings, we're going to just click on the different type of process that we want. So let's just try the standard one right now. So I'm going to click standard, and nothing's changed yet. To set up the camera, I'm just going to click the optimize button, and the software is going to set the binning. It's going to set the exposure and the gain for us automatically. So you see it says optimizing camera, and then it actually is going to go and collect the background for me automatically, and we'll see what it resulted in. So the standard on this particular tool has decided to go with a 2x2 binning. It set the exposure and the gain. And if I look in image processing, you see it set the standard recipe. So it's doing static background and the histogram normalization. Another thing that it did is it turned on snapshot and scan averaging. So it's doing actually eight individual pictures for every pixel, and it's going to average those so that it reduces noise in the camera. Now this is all great. It's probably going to work really well, but if you look up here, the optimization, or the so-called optimization, has now decided that we're going to run at 30 frames a second, but because we're doing eight frames per pixel, our actual speed is going to be a little under 4 frames a second. So now if I go up here and I click collect map in the same area with the same settings, you can see that my map is running painfully slow. But I bet if I look at my picture here, you can see that the quality of the patterns showing up on my camera is really good because it's averaging 8 of them per pixel. But I don't know, you're going to have to decide, do you want to run really slow with really pretty patterns, or do you want to get your data and get off the system without taking all day? To stop a map, I'm just going to go up here and I'm going to click the collect map button once, and that terminates the scan, and then we can click finish. So let's try a different optimization. Let's try here fast. Let's see what that does. So I'll click fast. We'll click optimize, and again, it goes through and it sets up the camera for you. And okay, so for the fast one, it's doing 5x5 binning. And if I look at my settings down here, it's doing just 1 frame, and it's running at 258 frames a second. So, it's arrived at pretty much the same conditions I started out at when I manually set it up. And in the recipe, it's still using the same standard processing recipe. So now if I hit collect map, we should see the same result as when I set it up. Basically no difference. So let's stop that. Again, I don't want you to, the point of this video is not to watch us collect data, it's how to set it up. Let's try one of the other ones. Let's try ultra fast. Let's see what that does. So we pick the recipe, we click optimize, and so this one is doing the 10x10 binning. So now we're running at the 460 frames a second maximum, and still everything's the same here. It's still doing one frame only. Let's see if this actually works. We'll hit go. And yeah, it's actually, on this particular sample, it's actually indexing something. If we look at the picture quality, though, you can see the quality is not fantastic. But for some of the bigger grains of copper here, it's able to index them. So you may be able to use these really high binnings values. You may not. All right, let's stop that. Let's look at one of the other auto tools on here. So I'm going to go back to manual setup, and let's go back to 5x5 binning, and I'm going to turn off my image processing recipe, and I'm going to reset my gain and exposure the way that I like it. So something like this is pretty good. Okay, so I manually set up my camera. There is an auto background capture feature down here. So it says capture background smart or SEM area. Right, I just showed you, I go to the image processing and I click capture background, and then I apply the recipe this way. You can also do it with these tools. So if I click SEM area, then whatever my SEM happens to be viewing, it will scan over that area to record the background. So I click SEM area, it captures the background for me, and then I can go and I can hit standard and apply it. That it just saves, it's just sort of a different route than going down here and hitting capture background. Now, if I click smart, it actually is going to drop the magnification on the SEM. I think it goes to about a quarter of your field of view, and then it captures the background. So the idea is to capture more grains. So let's see what it does. So right now, you can't see this, but my SEM is at 20,000x magnification. If I click capture background smart, my magnification went to 3,334x, and it acquired the background. Um, Now, that's not always a great thing. If I turn on my background subtraction, it it's probably not really good. And the reason for that, if I show you, let me go back to my fib screen. Um, right, this is my sample. My sample, the area that I want to analyze is only this little end of the fib grid finger. So if the SEM drops down to 3000x, so in this case it drops down to about here, and it tries to capture background, there's a whole bunch of area in the SEM that's either no sample at all, or it's the top surface of the grid finger where the background is not going to be the same as the EBSD surface. So be careful with this smart one because it does lower your magnification quite a bit. The SEM area one usually works as long as you know your SEM is at an appropriate magnification to capture a lot of grains. You can just click SEM area, but again, be careful there. Looks like I'm getting a little bit of contamination on this grid. I probably should have cleaned it before I mounted it, or maybe run the plasma cleaner. Fortunately, that's not going to hurt us today, but contamination could be a problem on EBSD. Okay, so let's look at some other parameters that you might want to look at for tuning your analysis. And let me zoom in a little bit and just go back to where we were. Okay, so we have we'll click SEM area. Let's redo the background. Standard, we'll just leave it on standard, and that should be fine. Actually, it's not fine because I think I acquired, yeah, I forgot to turn off the image processing. So because I already had background applied and then I acquired a background a second time, I'm double subtracting my background, which isn't right. So I need to change this to none, then click SEM area, and then I can turn on the standard recipe, and that should hopefully look better. It doesn't though. Maybe the contamination is becoming too much of a problem here. Let's just move over a little bit to a clean spot. Say none, SEM area. Let's see if I slow it down. Yeah, this is a little better. Okay. So if I go to my image processing, I'm using the standard recipe right now. The other recipe that's in this tool is the enhanced. And what the enhanced adds is, in addition to static background, it adds a dynamic background subtraction. Oop, I just realized you can't see anything that I just showed you. We're going to have to back all this up. Okay, sorry about that. Where were we? Okay, yeah, we were set up the camera. We have our image processing to none. We capture our background. So if we go over to the recipes, we have the standard recipe, which is these two functions, static background and intensity histogram normalization. The other one built in is the enhanced. So if I click on enhanced, it adds this step called dynamic background subtraction. Sometimes this will help, sometimes it won't. If you want to see the effects of these things, what I generally suggest is go to the custom option, and then you can click modify and you can actually build your own recipes here. But this is also a nice tool for seeing what these actually do. So the image on the left is our raw camera display. The image on the right is the process display. So let's just go in here and we'll choose, we'll just duplicate the standard recipe. So it's going to be static background subtraction. So we'll click on that and I'll click add. And you can actually see there's some parameters in here you can tune. You can tell it how many frames to average. This is for when you capture the background. So there's a capture and a load button here so that you don't have to go back out and hit capture background out here. And then the balance is going to tell the software how much to subtract from your image. So you can play around with this slider and you can see it controls the histogram value of your image. Now, right now my SEM is scanning really, really fast. Generally, when I go to set this up, I slow the scan speed down so that I can actually see um, the patterns in my live display here. So let's play around with the balance here, and you can see that if my balance is too high, I get no image here. So maybe, and if my balance is too low, I also don't really get a good result. Let's just put it somewhere maybe like 40. I think 40% is the default value, which as you can tell, it works pretty well. Maybe a little higher is nice for this case. Now then, the other parameter that is added with the standard recipe is the intensity histogram normalization. So if I add that, you can see that this gives you a brightness and a contrast slider. So now you can tune your contrast and brightness of the image to try to make it more suitable for analysis. So right now I've essentially duplicated the standard recipe, but by doing it this way, you get the ability to control this balance, which maybe that is helpful, maybe it's not. So we hit OK, and now over here I have a custom recipe loaded with these parameters. If I want to see what happens when I add the dynamic background subtraction, I can add that. Now I added it and it's out of order. The dynamic background subtraction in the enhanced recipe actually goes after static. So to change the order of the processing, you click on a step and you can either move it up and down in the list. So I'm going to put dynamic second, and this one has a balance function as well. So we can tune the balance around and see what it does. Um, on this particular sample, I don't think it's going to help much, but sometimes it makes the patterns run a little nicer. It's something to try. Then there's a lot of other things in here that you can play around with. There's some smoothing filters. Um, you can do static background division instead of subtraction if you think that's going to help. The intensity histogram stretch is another sort of brightness contrast function, but it just essentially pulls the histogram to maximize, from 0 to 255 for you automatically. You can do kind of the same thing with the normalization. The nice thing about the stretch function is it's dynamic. So if your beam is moving around and your contrast is changing from one area of a sample to the other, the stretch will adapt as it goes, which is whereas the histogram normalization is a fixed brightness and contrast operation. Um, Generally, I find that the standard recipe should work for almost all your samples. If you can't get the standard recipe to work, then usually your sample prep has got problems. So either the polishing is not good, or the sample's deformed, or it has contamination on it, something like that. Because generally, this one is good. The one time I don't use standard that I'll talk about is if you have a single crystal sample. Um, in single crystal wafer samples or in TKD, you run in this a lot too. You can't do the static background subtraction because you can't get the beam to scan over multiple grain orientations because you only have one grain. In that case, what I generally run is a modified recipe that is dynamic background and intensity histogram normalization. So I'll show you that one. So if I go to custom, let me remove these settings. And I'm going to go and do dynamic background subtraction first. Now, with the dynamic background only, uh, what it's basically doing is it applies like a blurry filter to your picture, and then it inverts the contrast and subtracts it from the picture. So the you can tune this number of passes and you can tune the balance. And the idea is that you can try to get rid of some of the background this way. And again, you want to be looking at your live display so you can see the result of what you're doing here. But you can tune these the passes and the balance around. Now, one thing I generally see is that you see if I make the balance really low, you get sort of this dark perimeter around the camera view. And as you raise the balance up, it gets more uniform. And then at some point you get like an inversion here. So now the outside is really bright. So I usually set the balance kind of somewhere in the middle there where you get more or less a uniform grayscale across the whole field of view of the camera. And then you can also tune the passes. I haven't found that this helps too much, but I think the default is 10. I usually leave it there. That's usually fine. But you can play around with that. And then after you've set your dynamic background subtraction, then I'll put the intensity histogram stretch on there, or the normalization, depending on what you want to control. And then that will tune your brightness and contrast values. Um, I'm going to think I'm going to add a little bit more. I'm going to play around with this balance a little bit more. All right, I like that a little better. Okay, so I hit OK. So now I don't have any static background subtracted, but let's see if it runs. So if I hit collect map, um, and you can see the quality is not great, but it is actually running and it's indexing. At least the bigger grains are working. Not as pretty as the standard recipe, but when you're working on single crystal or very large grain materials where you're doing your analysis all in a single grain, this will work fairly well to get you patterns, because you won't have a background subtraction reference. Um, I use this same setup in TKD a lot as well. Um, let's see, what else can we talk about? Camera position. Let's see, this is insert and retract of the camera. Image area, we've talked about some of this, right? You've got this mainly applies to the SEM image, but you want to make sure that your stage tilt and pre-tilt angles are correct here. The forward scatter detector is an imaging detector. It lets you acquire images um, of the sample surface, but because the beam is scattering off the sample, you get a lot of topographic contrast, and you can also get some grain structure contrast. Setting these up it's really finicky. Um, maybe I'll show you how to see if I can get it set up here later, but I want to spend more time on the other parameters first. Um, EBSD mapping. This tab is used to set your map dimensions. Um, so there's two ways in the mapping tab. When you grab your SEM image, you can set your EBSD map by moving this little green box around. So click and drag. You can set it where you want. You click the bottom right, and you can make it bigger or smaller. And it shows you the dimensions here in X and Y. You can also set this in the EBSD mapping tab explicitly. So you can set your starting coordinate in microns for X and Y, and then you can set your scan size in microns explicitly. You can't change step size here. You have to change that up in the collect map tab. Um, there's different types of different draw types. And scan types. So if we go to freeform scan, this lets you draw kind of odd shaped maps. So say you have a feature that's not square or rectangular and you want to scan on it without collecting a bunch of extra points, you can make kind of arbitrary shaped maps. Um, the Let's go back to normal here. That would be the rectangle style. The grid type, you can do either hexagonal or square grid. By default, you're going to scan in a hexagonal array. So that means that every pixel is shifting back and forth. Here I can show you if I let me do a custom map, and we'll do a really big size. Let's do like 20 micron. Or no, that's going to be too big. Let me do 1 micron. I think that'll show it. Oop, no, it did not. Oop, I did 1,000. We don't want 1,000. We want one. Okay. Okay. So here you can see the when the pixels are so big, you can see that it's actually a hexagonal array of points. But if I change this to square and do the same setting, now we get a square grid of points. Some analysis software requires square points. I think the Dream 3D analysis and maybe the cross-court softwares, I think they need square grids. I don't know for certain on that. The hexagonal grid is supposed to be better at capturing grain boundaries that happen to be either vertical or horizontal aligned with the scan direction. That's why EDAX uses it. But you can change it in here, either hexagonal or square. The resolution is, this is just the resolution of the map, or it's the step size. So that's the same thing up here. Is you have your coarse, medium, fine, and custom step sizes. You can choose whether or not to index the patterns. If you know you're going to do post-processing, you can turn this off, and it increases your scan speed a little bit, especially if you're running in a processor limited scan condition. But most of my users are going to use the indexing solution from Teams, so they're going to leave that on. But you can turn that off if you want to. You can choose whether to save the Hough peaks. The Hough peaks are used to find the EBSD patterns. So if you save those, you can go back and re-index your maps later if you think the indexing solutions are wrong. If you choose to discard the Hough peaks, then you can never rebuild the map. So whatever results you get off of this scan is what you're stuck with. So normally that's going to be left on, but you can turn it off if you want. And then if you choose, you can save the patterns. So by default, Team does not save the individual EBSD patterns, so the pictures from the camera. It only saves the location of the Hough peaks. For some of the post-processing software packages, you need the actual images from the camera. So you would have to turn this on, and then you can choose what file format you want to do. There's this .pattern file, UP1 or UP2. UP2 is the one that most people use, to my knowledge. And I think the newer version of Team, you can also save TIFF files in addition to these three formats. Be aware that if you save the patterns, it makes your file gets really big really quick because you're saving a TIFF image for every single pixel in your map, and it's all buried inside this file. You can pull it out later. So that's the EBSD mapping tab. Specimen stage, this is just reading the stage of our microscope. You can actually move the stage around in here if you want to. I generally don't use this feature, but you can if you wanted to step around in the software. You can just put in different coordinates and hit go to, and it'll move around. Annotations are, overlays on your SEM image. So if you want, you can change these parameters. This is another feature I never bother with. tEBSD or TKD mode. If you're working on a thin sample and you're working in TKD type geometries, you have to enter the TKD mode, and you just open up this tab and you click on the little checkbox here so that it's in TKD mode. When it's in this mode, it does not read the stage tilt anymore. You have to tell it explicitly what angle your sample is with respect to the SEM. So in this convention, if your sample is flat and perpendicular to the SEM, it would be at a 0 tilt angle. And then as your stage moves around, you would change this angle. So for instance, you could put in 20 degrees here if your stage was tilted up 20 degrees. I can't demonstrate TKD mode right now because I don't have a thin sample in the chamber, but once you're in TKD mode, then everything else proceeds as normal to set up the camera and acquire your data. Um, the last parameter in here is the Hough parameters. Um, I'm gonna, I'll, I'm not gonna pretend that I'm an expert on all this stuff, but I'll show you what some of these values can do. I'm gonna change my SEM real quick though to a little bit different setting, just to get a little bit more contrast on this, so you can see what's going on. So if I go back to my SEM here, I'm gonna go to a little bit higher beam current. I'm gonna go to 26 nanoamps, so that I can just run a little bit faster. All right, we got to focus. All right. All right, so let me go back to team. All right, so we have to because I changed my beam current, I have to redo my camera setup. So I'm gonna stick in manual mode, but I'm gonna drop my binning down to 2x2 because I want to see a lot of small pixels here. And let's change it to no image processing. Like I said, you have to do that. I'm going to set my exposure. Uh, I have to go fairly high exposure because the binning is so small. There's different exposure ranges here. I don't think I showed this, but we'll go to the next longer exposure setting. And I'm going to drop the gain down quite a bit because I want this to be a real high quality picture. So no gain. All right, so now let's go into capture our background. Oh, I don't need 1,000 frames here. All right, capture. Oh, that's pretty slow. And we'll put on standard processing recipe. Okay, so now let's go over here to a tab we haven't looked at yet, which is the survey tab. So I'm going to click on survey, and this allows me to move the beam around and see the results. So you can see the little green dot in the middle is where the beam is, and I'm getting a live view of my camera. So if I click and drag this around, I can kind of explore what my grains look like, and I'm looking for just like a real pretty grain. Okay, here's a good one right in the middle. So I'm just going to let go of the mouse, and then it acquires a pattern, and it shows me this indexing display. Now, the way that the software indexes it is it looks for these bands. And over here on the left, there's a bunch of little tools. This first one says hide indexing solution. So I'll click on that. So here's my raw camera display. So I can turn on and off the solution. The next one down shows the input bands. So these black lines are the result of the Hough transformation looking for bands. So if you're having a hard time getting your indexing to work, I would suggest looking at this first. These bands should line up with the actual bands in your sample, right? So if I look at it just by eye, I can see where all the bands should be, and I can tell that for the most part this is lining up pretty well. If they're not, we can go and look at the Hough settings. So down here on the bottom, I click Hough, and I can play around with these. Now, right now, there's, I think, eight bands are being detected. If I need more bands, I can change the maximum peak count value. So let's say I want 10 bands. So I click on 10, and then I'll go up here and click go. And now it adds, you can see it's added another band here that wasn't there before. That may or may not help. It depends on whether the software can actually find the bands. But if you have really good contrast and there's a lot of bands visible, then adding this, increasing this number will improve your confidence index. if I make it really small, like if I go to 4 and hit go, um, you can see now that it's only looking for 4 bands. So it finds the 4 most intense ones. And this will probably make my confidence index get worse. So right now it says it's 0.75. I didn't look at what it was before. Let me put it back to 8 and hit go. Actually, it's 0.61. It's actually worse now, but anyway, you can play around with that value. If I want to see what the Hough transformation looks like, there's this full display button down here. I can click on full display, and this shows me the actual Hough transformation. So the Hough transformation is used to let the software find these bands. So um, if you want to look at the math involved, what I would, as a starting point, let me close this for a second. Go to the help guide, which is, it's always good to look at help guides, right? But go to the technical reference section in the help guide, EBSD, and go to the indexing section and read through this whole section, and it does a pretty good job of explaining what is going on with the Hough transformation. So the Hough, I'm just scanning through. I'm looking for the Hough part. Where is it? Indexing. Maybe that's the wrong spot. Somewhere in here, there's a spot about the Hough. Yeah, okay, here. So the Hough transform, I'll just click on this link. Where did it take us? Okay, into Hough transform. So it's a separate part in the help guide. But anyway, this is the mathematics of the Hough transform. You're basically turning straight lines into points in the Hough space. And then the software finds these points because it can find those better than a line. So the Hough transform turns this into this, and the conversion process may or may not help you in terms of getting your patterns to run. So the parameters in here, if I go back to full display, um, the EBSD camera is a round image. We can tell it basically what step size in a radial coordinate and this row and theta coordinates to turn this into this. So if we change our pattern theta step size, if I make it say 0.25, it improves the resolution, or at least it lowers the pixel size in the Hough transform, and that may make it find patterns better. If we go the other way, if I make it really big, you can see the Hough transform gets a lot blurrier because the pixel size is bigger. You can also change this pattern, this bin to pattern size. So if I make the bin size really small, you can see the Hough transform gets really coarse. And if I make it really big the other way, then it gets really fine. The little crosshairs here are the bands. So ideally, we want to have a crosshair show up on all these bands. Um, if you ever get messed up, there's a restore default. You can always put it back to where it was. If you have defects on your camera, say there's like a scratch or something at the top or the bottom, you can exclude some of that by using this row fraction value. So you see if I change this, it puts this little circle on here and it only looks at the information inside the circle. So if you're getting artifacts, like for instance here in the Hough transform, there's this kind of like bright band down at the bottom. If we want to exclude that from the analysis, we can tune the row fraction value to kind of chop that off. Um, by default, it won't include the whole camera anyway, but you can always do that. And you see this blue band is like right near the edge, so maybe if I want a little bit better view on that, I could actually make the row fraction a little bit bigger, and then maybe you would catch that with a better result. I don't know. The other thing you can do is this vertical bias function. Um, in the pattern, there's always going to be some spot where there's better quality. Here, let me just show you. If I go back here to this view, turn everything off. you can see like up at the very top, it's kind of blurry. At the very bottom, it's kind of blurry. It's really nice in the center right now, but this changes with working distance. So you may find that like the really sharp area of your patterns might be more to the top or to the bottom of the camera. So if you tune this vertical bias value, you can have the software focus more on the bottom of the camera or more at the top of the camera, and that may be something that helps it index. With a good quality sample though, I usually don't have to change any of this and just use the default value, and it's usually fine. Um, some of these parameters do have a processing speed penalty, so it'll tell you here like how many milliseconds it takes to process. So right now it takes 6 milliseconds. Um, if I were to change the binning, so maybe if I go to 120 instead of 80, or what was it, 90, 96, you can see it adds 3 milliseconds to my processing time. It's not a big penalty here, but if you're running hundreds of thousands of points, that might slow down your analysis to where you can't get your work done. Uh, all right, let's see. Is there anything else I want to talk about? Um, let's see, in survey mode, let's see. Yeah, this just shows you the result of a single point. So you have your indexing solution here. Actually, this one's not matching up super great. If you wanted to try to get these to fit a little better, so you can see here like the the 022 and the 202 lines are lining up fairly well with the pattern, but this the 131 line right here is not lining up real well. Probably because I could be on a grain boundary here. There might be two patterns overlapped, but if you have a real good quality pattern, there is a tuning function that you can click tune result, and the idea is that it adjusts some of the parameters to try to make this fit better. Um, you don't want to tune on a bad pattern though, so I'm not going to use that. I'm going to go back to I'm going to see if I can find a little bit prettier pattern. Like here, this is a pretty good spot. Let's see. Yeah, that's pretty good. I'll let go right there. And now if I say yeah, now the bands line up pretty well, and I say tune result, we might see our confidence index get a little better. So I say tune, it adjusts slightly, confidence index gets better, fit got better. Didn't really change the result of the orientation much, but gives a little bit better statistics. Other tools that are in here are you can change the indexing mode, whether you're using either Hough mode or the manual mode. I don't really know why people would use this, but the way this works is if you go to manual indexing mode, you can draw lines on the screen that line up with the bands that you can see. So maybe the software can't ID them, but maybe you think you can. So you can put your own lines on here, line them up uh, like this, and then you can hit go, and it will try to fit a solution to the bands that you put on there. Um, Again, it's going to be kind of the same result as the Hough mode because I can see the bands really well. There's an image processing tool in here. If you want to play around with these filters, you can do it out of this wizard. It doesn't apply to the camera setting though, it's only to that particular image. This is turn on the wireframe if you want. There's this band detective thing that you can turn on, which just shows you like the overlay. Now, if you want to save this as this particular point, you can say send a project. So if I click send a project, that will then go over here as this EBSD spot one. So then I can show it to people if I want to. And then if you click save, it will save the tuning result as well as this the work you did on this point. Sometimes tuning the analysis will allow your scans to work a little better. If the camera's calibrated really well by your staff, then you shouldn't have to do this much. But if we hit save, that will save the tuning result. So then if I run the whole scan again, it might be a little better quality. Um, Let me go back and just take an image or a map here so I can show you how to export your data. Let me go, I'm gonna hit release beam. We'll go to mapping tab, and I have to reset up my camera again. Let me just tune my SEM focus a little bit here. All right, so EBSD camera, I'm gonna run, so again, I turn off my processing recipe. Let's go 6x6 binning. I'm going to turn my gain all the way down. I'm going to set my exposure. Oop, I need a different exposure range. I want the really short one, the 0 to 10. And I want to find that point where my frames start to drop off. 3, yeah, right about there. I'll tune my gain if I need it, but I don't need much gain. Acquire my background. Turn on my recipe. I can see my patterns look pretty good here. And then let's take a map. Now, I'm in the custom mode right now. If one thing to watch out for is the coarse, medium, and fine will set your step size for you based on your field of view. So these aren't consistent values. So if my coarse setting right now is doing a 0.3 micron step size, but if I were to go to lower magnification, this might jump to like 1 or 2 or 3 microns. So a lot of times when I'm collecting data, I like to stay in the custom mode because then you can explicitly tell the software what step size you want to use. Um, in this case, I'm going to use a very small value, maybe like 0.1 micron. And let's hit go and they'll see what this does. And I am perhaps zoomed in too far because the copper grains in the sample are really small. So let me lower my magnification a little bit. We'll redo our image area and try this again. All right, so I'm not getting a real great result here, probably because of this is really close to the edge. Um, no, it's looking a little better now. It's just some kind of edge effect there. This sample has really small grains. They're close to the resolution limit of the EBSD technique, so that's why a lot of this looks a little bit uh, fuzzy. All right, I'm going to stop it. This is good enough for me. What I want, I'm going to hit stop. I'll save the data. It gives you a summary of the results here. And I hit OK. And then if I go up here to finish, there's a send to OIM analysis button. So if you want to do any kind of analysis on the system, you can say send to OIM, and it opens up OIM analysis. So then you can look at your data, and you can process it with however you want. So you can look at the results here and do anything you want. Um, the other thing you can do is if I click finish, there is a report tab that shows up, and you can click quick report, and that creates a little Word document that has the SEM image, it has the IPF map and the IQ map. We don't usually use these much, but you can make templates with your own setup here. So it can process the data that you want. There's also another in the report tab. There's a send to OIM, and you can tell it to automatically pull up certain things. So let's say I want to see grain size, and I say send to OIM. You say it pulls up all the grain size, like the standard grain size tools, automatically load when OIM analysis opens up. So then you can look at your data right away. Um, you can always do this manually if you know how to do OIM, but it's just like another tool that's in here. Uh, And if you wanted, you could put these tools could be loaded into a template, and you could have these custom reports run out of the software if you want to. If we go to the review data tab, this just has the report function, which if I double click, open this up, go to review data, I can say run the report. Again, it's the same thing that's in the end of the mapping tab. Now you can also rebuild the data. So let's say I use the copper file for this one, but maybe this is aluminum. I did it wrong. I could go in here and I can say, don't use the original phase, use a system phase, and I can go into phase list and I can change this. So let me remove the phase. And let's say I think this is actually, let me not, I won't use aluminum because that's the same, it's really close. Let me use, what's a cute, like a different structure. Let me do like salt. I'm gonna do sodium chloride. This is gonna index really bad, but anyway, so I'll say I think this was, it's a cubic rock salt structure. So I'll put that in there and hit OK. So now if I say rebuild the map, it will reprocess the orientations using the different structure file. And maybe this, this way, then it could be more correct if you picked the wrong file to begin with. Um, so that's how you reprocess the data. I don't think that applies. If I go back to my profile, yeah, it overwrote my profile value. So it, if I want to put that back to copper, I can, remove this and change everything to no, copper, search. There we go. And then if I look at over here in my project tree, I have my two maps. So the OIM map 1 was the original data. So if I double click on it, it loads. And the rebuild is indexed using the wrong structure file, in this case, using the sodium chloride file instead of copper. And you can see it's not as good because the structure file doesn't match. Um, all right. The last thing I'll just demonstrate here, because this is because we have the fib, is in this particular example, I can clean up my surface. So if I look at, let me go back to my fib view. If I look at my surface now, you can see I'm getting some contamination on the surface. If I want to, I can polish that off by fib, which is useful. Um, and then I can run my maps again. If I'm going to move the sample to my fib spot, though, I need to retract the camera before I do that. So we go back to our software for team, and we'll pull the camera out. EBSD camera position, back it up. Then I'll go to my fib spot. And I'll just use the fib to chop off the face. And you can see the contamination is now gone. And this will probably be, there we go, I'm gonna stop that. This will be a lot smoother. I had used some low voltage to try to polish the sample, which is why it was a little rough. So now let's go back to our EBSD spot. Put the camera back in. Okay, so the camera's in. Let's go back to team, and let's just see if this looks, if I can get a really nice, pretty scan over the whole thing. Focus. So we have to set up our camera again. Here, this time, let's use kind of a yeah, we'll stay at 6x6, but I want to reacquire my background just in case something changed. Standard. All right, so we'll say mapping, image area, and we'll use the freeform mapping this time. So we'll do scan type freeform, and we'll draw, just do this whole thing and see what it looks like. There we go. And then our map, I always like to start with a fairly coarse step size if it's going to be a big area. For this one, maybe let's do 0.5 micron. Just make sure everything's set up right. Patterns look pretty good. Quality of the map is terrible though because my step size is too big. So the beam is hitting a lot of grain boundaries and that causes it to not index very well. All right, but I'm pretty sure that this is going to work. So now let me go and I'm going to change my step size to a really tiny value. Let's do maybe 20 nanometers. I don't know. Let's see what this is going to take. So 20 nanometers, it says it's going to take 4 hours to run. I don't have that much time, so let's abort that. Let's try a little bit bigger. Let's try 100 nanometers. That's going to take 13 minutes. I think that's probably reasonable. And we can see what the whole field of view looks like after cleaning it up with Fib again. Now, I'm not going to make you watch all that. I'm going to pause the recording for a second, and then I'll just show you the final result when it's done, and hopefully it looks pretty good. Pause. So it's about halfway through acquiring this map. I'm thinking the quality of the patterns look good, but the grain size is really small, and it's not picking up a lot of the really fine stuff. I think if I wanted to do this for real, I'd probably have to do a smaller step size, and that's just going to take too long. But hopefully you get the idea of how to set up everything for the analysis. So I'm gonna stop this and shut the system down so that this video doesn't take forever. So we'll just turn that off. Hit finish. So the shutting down the system, we just need to retract the EBSD camera. So I'll go back to camera position, hit retract. Camera's coming out. Right, we can confirm that it is retracting. Right, camera's out. And then for the team software, I'll just make sure I export my data. So I'll go to the project tree and I'll say export. You can choose what data you want to export. You can tell it if you want to include the pattern files or not. So normally you would, so that you could reindex later. You can decide if you want to delete your data at the end. That would be deleting the local copy. And then I guess you can password protect it if you want. So you hit OK. You tell it where you want your data set to go, and it will be this zip folder. We hit save, and then that will export all of the data in a format that can be moved. It's not the quickest software when it comes to exporting data. So it asks you, are you sure? And say, okay. All right, so then the data is gone. And then I can close team. Now that data, I just exported it to the, where did I put it? My documents. So the data right now is sitting in this zip folder. If you open this up, you can manually click your way through these files. So go all the way into EBSD training, copper post 1. Here's my different areas. And then the actual scan data for that last map I just acquired would be this OIM data set right here. This map, it's got the date and time acquired. So really, the only data I really need to take with me is this file. But if you want all the stuff that goes with it, then you can take the whole zip folder. Um, but you may decide that that's just a lot of extra information to bring with you. And then in terms of shutting down the fib or the SEM, it would be the normal shutdown procedure. I would suggest you set everything back the way you found it. Put your specimen pre-tilt angle back to 0 so you don't confuse the next person. Turn off your dynamic focus, and then put your stage back to 0 and vent the system. I hope this video will help some of you when you go to set up EBSD maps. Um, Please feel free to reach out to me if you have any questions. I'll try to answer them. Um, and good luck with your analysis. Bye.